Today, this video, we'll call it Cardio 2. It's be a shorter one. We'll just pick up where we left off and talk about a couple more things about the valves. So we were, I think last time, looking at the right atria and the right ventricle. Right atrium, right ventricle. And again, we looked at the valves. Again, valves only allow blood to move in one direction. And one of the set of valves on the right side of the heart between the right atrium and the right ventricle. This is the tricuspid valve. And then the other valve on the outlet between the pulmonary trunk and the right ventricle. There is the pulmonary semi-lunar valve. Called the pulmonary valve, pulmonary semi-lunar valve, either one will be fine. Again, this one is tricuspid valve on the right side, or you can call it the right atrioventricular valve, that's fine. Now, as we mentioned last time, when the blood moves from the atria to the ventricle, tricuspid valve closes. Sorry, when the blood moves from the atria to the ventricle, tricuspid valve is open. When the ventricle contracts, the pressure gets higher in the ventricle. It tries to move back into the atria. That closes the valves. That is your first heart sound, the lub of the lub dub. Ventricle generates some pressure. Eventually, it forces the blood out into the pulmonary trunk. When the ventricle starts to relax, goes into diastole. Pressure in the ventricle will drop very low. Pressure in the pulmonary trunk is higher. The blood will start to backflow. That will catch the cusp of that valve, and that's your dub, the second heart sound. Now, just to mention a couple of things. Normally, when these valves close, they make a tight, watertight seal so the blood doesn't backflow. Again, you hear the noise because there's a little bit of vibration, but you don't hear much else in the heart. But sometimes, because of either congenital defects in the valves or perhaps rheumatic fever, and usually strep goes down and starts inflaming the valves of the heart. It's actually an autoimmune condition. But you might get a little scar tissue, and you can have some leakage in these valves. Now, let's say, for example, this tricuspid valve leaks a bit. So there's a small hole in it. Small hole in it. There. Now, that happens. Dry out my water. When the ventricle contracts, the valves will still shut, but now there's a bit of a hole in them. That's going to allow the blood to squirt through, it's like a little orifice here. It'll squirt through under pressure. This will create a noise. That flow is turbulent. It'll vibrate the tissue. You can hear it. At least with a little bit of practice and training. I've tried to listen to a few. I don't get them that well, but with practice, you can hear them. They refer to these as murmurs. So where they occur kind of can give you some indication of which valve is leaking or which valve isn't working properly. If you heard a lub swoosh dub, for example, that swishing sound would be that blood backflowing through that valve. And you can hear it. Now, you got blood going the wrong direction. This isn't the best setup, but do you need to fix it? Well, it depends. As you mentioned earlier, you have a lot of cardiac reserve, a little bit of blood leaking backwards. Not a big deal, you can compensate for it. If these leaks get bigger and bigger, do you eventually have to fix it? Well, I guess the answer is it depends. Again, you can compensate for a substantial backflow, substantial leak to these valves. The heart could still keep the blood moving forward, keep you functioning. The problem is, if there's blood moving backwards, the heart has to work harder to keep the blood flowing at the appropriate amount. And of course, that means it has to work harder. And when a muscle works harder, what does it do? It gets bigger. It's hypertrophy. So what they'll look for, if you have a bit of a murmur, and they don't notice anything in the way of changes in the ventricle to speak of, they might leave it. Because again, changing a valve, it's open heart surgery. I think they still crack your sternum, open you up, and it's kind of a pain in the neck. So if you don't need to do it, we don't want to. But if the leakage gets bad enough, the ventricle will be working harder to keep the blood flowing, and you will see increase in the size of the ventricular muscle. They call this ventricular hypertrophy. It can be picked up with an EKG, X-ray, a number of ways to detect it. The problem is that you might think, well, great, my ventricle's bigger, I can pump all kinds of blood. Well, no, remember, cardiac muscle cells cannot make ATP anaerobically. So as the ventricle gets bigger and bigger, basically its volume is increasing very rapidly. That coronary blood supply that supplies all the cardiac muscle cells with oxygen, it may not keep up. And you can get to a point where the ventricle is getting so big, you can't supply it adequately with oxygen. That's going to start to degrade some of the cardiac muscle. So the valve has to be replaced. And it could be either one. I'm just using tricuspid as an example. And I will tell you, typically when valves go bad, it's not these. It's the valves on the left side of the heart. I'll explain why next time. Right side of the heart usually isn't under as much stress. These valves, well, they can fail. It's less likely. So if the valve's leaking, you got to fix it. Yeah, they got to go in, crack it open, put a replacement in there. What do they use? Basically, you got a couple of options. You can use a cadaver valve, off of a dead person that's donated. The valve is still alive, by the way. It's not like transplanting a heart. Valve's just epithelial connective tissue. They don't have the oxygen demand that the cardiocytes, the cardiac muscle does. So they can be stored for a bit. So you could use cadaver valves off a human, off a pig. They've used other animal valves. Pig heart's close in size. Depends on the size of the pig. You can put those in there. They work fine. The advantage of the live valves or the cadaver valves is they are living tissue, so it'll self-repair. There's no issues there. They stay nice and smooth. The problem with it, just like any transplant, is your immune system. So you might start attacking those own valves. So it's organ or tissue rejection. So they have to give you something to suppress your immune system a bit so you can keep the valve. On the other hand, they have some synthetic valves. I don't know what they make them with now. It's synthetics and nylon, Kevlar, stainless steel, plastics of some sort. They can put those in, cut out your old valve, stick in the synthetic. That works great too. The advantage of those, there's no proteins or glycoproteins for your immune system to recognize, so you're not going to have an immune response. The downside of synthetic valves, anytime you put something foreign in contact with the blood, it can cause coagulation, blood clots to form. If you got blood clots forming around here, of course, they can go through the coronary arteries, cause a heart attack, they can go up your brain, cause a stroke, lots of problems. So they'll typically put you on something that will reduce your blood's ability to coagulate. They often call them blood thinners, but they're anticoagulants. And so downsides to both. Of course, you take anticoagulants, then you have potential problems for bleeding because, you get breaks in the circulatory system all the time. Coagulation is what blocks them. If you're taking chemicals to reduce your blood's ability to clot, you're going to bleed more. So you can use cadaver valves or synthetic valves, either way. That's kind of it. So that was my short valve one. Now what we'll look at next time, we got one pump here, the right heart. We've done the ventricle atria. That's a pump. Why do we have two? And you don't need two pumps to move blood. One pump will move the fluid. In fact, let me stick up a little diagram here. You don't need to know this one. It's going to be a little hard to see again, but this, if I can get it in there a little bit. I need it over there. It's the far one. Check so you can see it. Oh, it's not great. This will do. Just real quick. Again, I'll cite this diagram. It's on your blackboard. You're not going to see it well here, but this is a fish heart. Fish hearts have one atria, one ventricle. Now, fish get along just fine. They have one atria, one ventricle. They seem to be living just fine. I assume out in the ocean, out in the ponds. Why do we have two pumps when the fish only has one? You only need one. And I was just saying, well, fish are small. No, whale sharks, man, 40 feet long, they'd be huge. What's the difference? Well, as we'll see next time, we have to have two pumps, the right side and the left side, because we got to do one thing that fish don't. Fish, well, they're no slouches. That's someone who can swim really fast in the water. I don't know what a manta ray swims at. It's like 60 miles an hour, something crazy like that. They're fairly active, but compared to a mammal, a fish's metabolism is way lower. Now, again, metabolism requires oxygen. So the higher your metabolism, the more oxygen you have to get to the tissue. And as we'll see, a single pump system, like you have in a fish, one atria, one ventricle, won't hack it. So what we'll look at next time is why we have a double pump. And I'll tell you ahead of time, the reason is so you can supply blood a much higher blood flow to the tissues. That's what's required to maintain a high metabolism. Mammals, homeothermic endotherms, like birds, also have a four-chambered heart. That seems to be necessary to supply the blood and therefore the oxygen that tissues need to supply the high metabolism of endothermy. That's it for now. I'll be back.